All right, what we're going to be looking at here in this lesson is permutations and combinations and how you figure out, well, how many could I have of either one? Now, just a little bit of background on what a permutation and a combination is. A permutation and a combination is kind of a way of organizing something. Maybe it's the letters in a word, maybe it's how many condiments you could put on a hamburger. Maybe it's a way of organizing, cars at a dealership to how many ways you could do something. The difference is that in a permutation or a combination, they're very much the same thing, except that the way in which we are going to kind of organize things in a combination rather than a permutation is that we really don't worry so much about the order in which they're arranged, whereas in a permutation that we do. Now, here, what you're noticing, first of all, it's giving you kind of a generic definition of what a permutation is. And again, here's that word, is that we're worried about the how things are ordered. But the formula that you see here is how we kind of calculate the number of permutations that something could be put through, where n is kind of the total number of things, and r is the number of specific things, unique objects in this case. So N and R, those two particular letters that you're seeing, they're completely arbitrary. They don't have to be N and R, but it does help to have some kind of uniformity, some standard, so that way across curriculums people kind of know what they're talking about. So N and R are generally kind of what you're going to be seeing whenever you're talking about permutations or combinations. And the capital P that you see right here, this that specifies that we're talking about permutations. When we do combinations, it'll be a C to specify that it's a combination. But let's go ahead and see what we're going to be looking at here. So again, permutation is kind of a way of arranging things in where we do kind of where order does kind of matter a little bit, and combinations, same thing, but order in which we arrange things don't really matter. Now, this is something that you can do on your calculators to help you with a little bit of the factorial math. But since I'm not sure what calculator you may be using outside of the one I might have in class, I'm not going to get too much into it. We'll focus on how you actually do the math anyway. So what it's telling you up here at the top, it says find the value of permutations by using the formula or computing the number of factors. Well, we're not going to use the calculator to compute the factors. We're going to actually use the formula. And what it's telling you here, we have the general formula for the permutations is we're going to say NPR is equal to n factorial over in parentheses, we're going to say n minus r factorial, where in this case, n is 12 and r is 7. So based on what we have here, we're going to say 12pr, and so here I wind up with 12 factorial over, in parentheses, 12 minus, oops, not paying attention. This is not r, that is a 7. So I'm now going to say 12 minus 7 factorial. Simplifying the denominator, I will get 12 factorial over 5 factorial. And expanding everything out in the numerator gives me 12 times 11 times 10 times 9 times 8, 7, 6, and when I get to 5 factorial I can stop because I have 5 factorial in the denominator also. And anything divided by itself always simplifies to be 1. Even if we continue expanding all of that out to 5, 4, 3, 2, 1 in the top and the bottom, because everything is multiplied, it all simplifies to just be 1. So really we're going to just say 12 times 10, or 11, 10, 9, 8, 7, 6, which means that we will have a total of 3,991,680 different permutations. With the given situation. So this is really just to see, well, how the formula works. Make sure you plug the numbers in and how it simplifies using factorials. And that's what we'll wind up with. Now, you definitely want a calculator to help you with the arithmetic. Definitely don't want to try and do all that multiplication longhand. But here, what we're really going to be seeing, this is the challenge for the types of problems that we're really going to be working with, is not so much, well, can you do the math? It's, can you get the right numbers to do the math? So what we see in the question, the word problem that we have, it says a local chapter of Mu Alpha Theta Math Organization will be electing a president, a vice president, and a treasurer. In how many ways can the positions be filled if the chapter has 15 members? Well, we need to identify, well, what is the N? What is the total number of whatever? In this case, we're talking about people to fill a job. And R is, well, the number of unique elements that we're talking about here is the number of positions. Well, here, looking at it, we have 15 members. That's given to us straight away. They're not giving us a number of positions, but we can count it pretty easily. We have a president, a vice president, and a treasurer. So that means that there are 3 positions. So here we have 15 members with 3 available positions. So when we identify those values, that's really going to give us 15 P3 for our formula. So I will wind up with 15 factorial over 15 minus 3 factorial. And we'll just run through the math here real quick. So 15 factorial in the numerator over 12 factorial in the denominator gives me 15, 14, forgot my 1, 13, 12 factorial. Once I get to 12 factorial, because I have one of those in the denominator, those wind up simplifying. So on your calculators, you'll say 15 times 14 times 13, which gives you 2,730 different permutations. And like I said, the math isn't so much the hard part, it's making sure that you can identify the numbers that go into the formula to begin with. So that was a relatively simple investigation that we're going to be doing. You'll have similar problems like it on your homework assignment. Some are going to be a little more obvious, some are you're going to have to think about a little bit more, but there's definitely something you can do, and if you have a hard time with it, make sure you come see me for tutoring. Well, here what we're going to be looking at is we're getting into something specific when it comes to permutations. Well, here what we're really going to be talking about, and it says it at the bottom, we're talking about distinguishable permutations. So let me give you a little definition about what they are. Distinguishable permutations. So a distinguishable permutation, if I could spit it out, is a permutation that produces a result that's different from the original. That's kind of what the definition is. Okay, so up at the top says, well, what if the elements of a set are not all unique? Meaning, like, okay, so in the last example, we saw people, okay, and that was a total number. Well, the positions that we had, those were, even though that, each position, president, vice president, treasurer, each one of those is different, they were still a position that needed to be filled by a person. That's why we're saying that they're unique. Well, what if they're not all unique? What if they're different? Okay. Well, this would be the kind of thing where maybe uh, we're talking about combo meals at a fast food place. Well, the number of things that we might have might be, well, we want 10 combo meals. Well, what if each set of that combo meal is different? Meaning, like, how many sandwiches that we might have, how many soft drinks available we might have, or how many, side combinations we might have, as far as maybe we have French fries or something like that. Those are things that are going to be unique, but still part of the set. Uh, so that's where we're talking about in the denominator. Here we have P, Q, and R. Well, so N is still kind of the overall thing, where P might be sandwiches, Q might be, I don't know, sides, and R is going to be kind of soft drinks or something like that. And again, P, Q, and R is really just kind of an arbitrary element here as far as the letters that they're using. A lot of times when I'm working out problems like this, instead of saying, P, Q, and R, maybe you want to use with, like, I don't know, the first initial of something that you're talking about. Whatever seems to make most sense to you at the time. So looking here, uh, this is what we're going to be looking at as far as distinguishable permutations. Something that's going to be different from the original one. Well, assuming that people are having babies that are identical and can't be told apart, how many distinguishable photographs can be taken of the 6 family members if they stand in a row in one set of family? Maybe there's a set of triplets. In another family, we have 2 sets of twins. So looking at our information for the first set, well, we have a total number of people, which in this case is 6. Well, we're looking at things that are kind of unique. Well, in the first example, we really only have one thing that's unique. We have a set of triplets. So we could say T for triplets, or we could say P simply because that's kind of what it was given to us. It's, like I said, the variable that you use is arbitrary, but since the formula gave us P, Q, and R, I'll go ahead and stick with them for the time being. But again, if another variable makes more sense, if you want to say T for triplets, then that's fine, go for it. In this case, we're going to say 3 because, well, 3 people make up a triplet. So according to the formula that we have, because I only have one unique set out of my elements here, I'm going to say n factorial over p factorial, which in this case simplifies to be 6 factorial over 3 factorial. And, expanding that out gives me 6 times 5 times 4 times 3 factorial over another 3 factorial. So those two things simplify. And that means I have 120 distinguishable permutations here. So there's 120 ways that we could arrange the 6 individuals in the family that are different from the original. And that's what a distinguishable permutation is. So now let's take a look at our second example. Well, still 6 family members, but now we have 2 sets of twins. All right, well, the total number of people that we have is still the same, 6. But now I have 2 sets of twins, and that's kind of the key word here. That's the thing that separates it from the original one, is saying that, well, we have uh, distinguishable permutation, or we have 2 unique things as opposed to 1. So I might have P to represent 1 set of twins, and so there's 2 people there. Then I might say R to represent this other set of twins, which again makes up 2 people. So that is kind of the difference between what we're talking about for a distinguishable permutation, meaning that I might have more than 1 unique element. So here I would set up the formula to say n factorial over p factorial times r factorial. If you wanted to say q, then that would be fine. Even if you wanted to say, I don't know, set 1 or set 2 and just said s1 and s2, it's whatever works for you. Here, substituting the numbers, we'll say 6 factorial over 2 factorial times another 2 factorial. Expanding everything out, if you wanted to, you could say 6 times 5 times 4 times 3 times 2. Now at this point, if you want to, you can stop and say 2 factorial, but I'll go ahead and say 1 because it's no big deal. And in the denominator, we can say 2 times 1 times 2 times 1 for the 2 factorials. And you can see 2 factorial really, since I have 1 in the top and 1 in the bottom, they are ultimately going to wind up simplifying out. That's why I was saying you could have stopped at 2 factorial, since we had 1 in the denominator that would simplify out. 6 times 4 times 3 times, well, that's it. 6 times 4 times 3 in the numerator gives us 360, and 2 times 1 in the denominator, well, that's just 2. So here I would wind up with 180 distinguishable permutations, or different permutations if you want to prefer. And there we go. So that's kind of what we're talking about as far as distinguishable permutations. We're looking at things that are going to be unique out of the elements that we have. So in the first example, we had 1 unique element, which gave us 3 identical people. So that's why I have P for 1 unique element and 3 for the number of people that make up that unique set. And in the second example, we have 2 unique things, and in each, so that's why we have the P and the R for the denominator to represent the 2 unique things. And since each unique thing had 2 people in it, that's why each one has the number 2 associated with it. Now here, this is very similar to the problem that we saw with the twins or the triplets. But they're not telling us exactly what they are. You have to be able to figure out, well, what is the unique element that we have here? Well, the number of letters that we have in this case is the total number of things that make up the word, in this case leave. So there are 5 letters that make up the word leave. Now looking here, we want to say, well, what is unique about them? Is there something that separates some of the letters apart from the other ones? In this case, I have 1 unique set, kind of like what we had with the twins. I have 1 set of twins letters, in this case the letter E, being repeated 2 times. Okay, so that's kind of what I'm looking at as far as the unique set there out of the elements that make up the letter or the word leave. So here I'm going to say n factorial over p factorial, which would give me 5 factorial over 2, and expanding that out, 5, 4, 3, 2 factorial over 2 factorial, which simplifies out. 5 times 4 times 3 gives me 60 different permutations there. Now, levy uh, is pretty similar for the idea of what we're talking about. We still have 5 letters, and in this case, out of things that are unique about the word levy is the fact that I have one unique element out of the 5, or I have one set of things that's unique out of the 5 that are there, and that's the letter E, the fact that it's repeating 3 times. So again, I'm going to say n factorial over p factorial, which gives me 5 over 3 factorial expanded out 5 times 4 times 3 over 3 factorial. So the 3 factorial simplify out, and I wind up with a mere 20 different permutations. Now, I'd like to introduce a little bit of variety here because as I'm thinking about it, well, we don't really have much to distinguish or much to separate one from the other. So I think yellow, maybe not yellow. I don't think that color shows up super well. Let's pick a different, pick a different color here so we can distinguish what we have. Let's just do black. I think black will show up fine. Let's say we have the word potato. Potato. Okay. Well, it looks like I'm writing more than one word there because I have too much of a space. Let's try it again where I can actually write it like it looks like a word. Potato. Okay, so same idea. How many different ways, how many distinguishable permutations could we have for the word potato? Well, in this case, looking at the words, we have P-O-T-A-T-O, 2, 4, 6 letters. So I'm going to say the total number of elements that I have are 6. Well, how many unique things do I have in there? Well, looking here, I have one set of unique things, and I don't want to use P because maybe you might think P is for potato. Okay, so let's get rid of that. All right, let's just say, well, O. O is a O is a unique thing because it repeats. The letter O repeats itself 2 times. Same thing with T. T repeats itself 2 times. So I do have some unique elements here. And unfortunately, those are the only unique elements, but that's fine. So here we would say uh, n factorial over O factorial and T factorial, because like I said, the letters are kind of arbitrary. You don't have to use P, Q, and R all the time, or even N for that matter. So here I'm going to wind up with 6 factorial over 2 factorial times 2 factorial. And I'll bring it back over here a little bit. Expanding it out, 6 times 5 times 4 times 3 times 2 factorial over 2 times 1 and another 2 factorial. Here again, just like in the previous example, things wind up simplifying out. And I didn't prepare this one in advance. I was just kind of thinking about it. So let me grab my calculator and we'll say 6 times 5 times 4 times 3. Well, I think I saw this on the same numbers as what we saw before with the 2 sets of twins to be, well, maybe potato wasn't the best thing in the world, but you get the idea. So here I'm going to get another 360 in the numerator over 2. Maybe next time I'm trying to think on my feet, I'll come up with something else. Maybe Mississippi might have been a better word here because, MISSI, we got a lot of unique elements in that one over 2. So that's really, again, going to give me 180 different permutations. So I'll do better, or I'll try to do better thinking on my feet next time. But I wanted to give you something a little bit different than one unique element between leave and levy. We really only had one unique element. It's just the different number that made up that set. So now let's talk about combinations. So like I was saying at the beginning of the presentation, combination and permutations are very similar to each other, except here in combinations, the number of unique elements that we have, the order doesn't really matter. And a little bit of math from a permutation essentially gives us this combination formula that we have here. And if anybody really wants to know, I'd be happy to show you where it comes from. But for our purposes, all we really need to know is what the formula is. So N and R, same thing. N is talking about the total number of elements that we have. So total number of something. And R in this case is going to be the unique elements. And in this case, the C separates it from the fact that it's, we're still rearranging things, but now we're specifying that this is a combination, not combo. And the formula is very similar to the fact that from the permutation one, except now instead of saying n factorial over the difference of n and r factorial, now we're multiplying in the denominator by r also. So the first example, again, is really just to see, can you use the formula okay? And that's not a big deal. The formula, the math is not really challenging. We're going to say, so NCR being n factorial over r factorial times n minus r factorial. And you can have the r factorial on either the left or the right of the parentheses, but I generally think it works better with it on the right because where most people are used to distributing or thinking that we have to multiply from left to right, even though we don't have to do it that way. So here I'm going to say 10C3. So I'd say 10 factorial over 3 factorial times 10 minus 3 factorial. Simplifying in the denominator gives me 3 factorial times 7 factorial. Expanding it out, now here some students may wonder, okay, well, what is going to, I don't need to make that, well, maybe I do, make that fraction bar so long. So what simplifies? That's what I'm thinking. I need to start expanding the numerator. That's why I really need to make that so long. So expanding out the numerator, the factorial gives me 10 times 9 times 8 times 7 factorial. And if we wanted to, we really could expand it all the way out down to 0, or I'm sorry, down to 1, so 7, 6, 5, 4, 3, 2, 1. And you're more than welcome to, and you'll see what's going to wind up simplifying out. So because I have a 7 factorial in the denominator anyway, that's what really tells me I can stop there, because anything I have in the numerator would simplify with the denominator. Now, you might want to think, well, would this 3 factorial simplify also? Because, Mr. Piercy, if you expand the 10 factorial all the way out, you get 3 times 2 times 1 also. But the thing is that it would already simplify from the 7 factorial, the 3 to 1, would already be simplified. So essentially what you're looking at here is that you do have 2 factorials in the denominator, and whatever the larger factorial of the denominator is will simplify with the numerator factorial. So the fact that 7 factorial is bigger than 3 factorial is what's really telling me I'm going to go ahead and stop there, but I still have to expand the 3 factorial in the denominator. And we'll see those two things simplify out. So 10 times 9 times 8 is going to give me 720 over 6. So here I would wind up with 120 different combinations. So there we go. That's how the formula works. And final example here as far as how combinations go, well, we'll say, okay, so some fancy French chef, Pierre de Guire, I don't know how you say that in French, Guire, whatever. Pierre, chef, award-winning chef, has developed 12 delectable, like that vocabulary word, like that verb, 12 delectable main course recipes for his restaurant. In how many ways can he select 3 of them to be represented in the culinary competition? So again, we want to know what is the total number of things here. In this case, the total that we have is 12 delectable recipes, but out of the 12, he can only submit 3 of them, which, wow, how do you, if you have 12 great things, how do you pick only 3 to really represent you as a chef, I guess? But in this case, we're going to say uh, from what we have, if we say NCR, that's really going to give us 12 CR. Oops, I don't know why I keep always wanting to write the R instead of the number. So 3. So plugging that into our formula, we're going to say 12C3 is equal to 12 factorial over 3 factorial times 12 minus 3 factorial. Simplify the denominator, and we're going to get 3, oof, my hand didn't want to cooperate there. Let me fix that. 3 factorial times 9 factorial, and because 9 is bigger than 3, when I expand out the numerator, that's where I stop. 12, 11, 10, oop, getting a little aggressive with the multiplication dot there, times 9 factorial over 3 times 2 times 1 times 9 factorial, so the 9 factorial simplify, and I'll continue up here on the right. And that'll give me 1,320 over 6. So that tells me there are 220 different combinations that Chef Pierre could wind up substituting, or I'm sorry, submitting to the culinary competition. So that is pretty much going to bring us to our conclusion of combinatorics. You could think of it as that way, where we're talking about permutations and combinations. And as always, any questions that you might have had for the presentation, make sure you write them down, bring them to me either in class or in tutoring, and I will be happy to work with you with whatever they might be. But until then, guys, thanks for watching. I hope everybody's doing well, and we'll see you soon.